Chandran, they will be almost similar. Like the level will be same. It won't be drastically different. Hardly there can be only difference can be instead of in some questions instead of giving the options, there can be a text kind of a thing. A bracket can be there, and then you just have to type the numerical values. In some questions it may be like that, but most of them will be multiple choice, single correct, and I think so it will be same because whatever I have seen in the NPTEL exams, they are all always follows the same pattern as assignment problems, so it won't be drastically different. I don't think so that negative marking will be, it won't be there, but I still ask will be a good choice to read the instructions before the exam. Like there will be, if it is if generally there are no negative markings in the questions, but if there is one, it will be mentioned in the instructions. And the exam will be online, but you have to go somewhere in a local college and give the exam. Means there will be an NPTEL exam center. There will it will pretty similar to what a GATE exam looks like. Like you will have a computer, you have to give the exam on that, but that computer will be present at somewhere at a centralized location, and you will be proctored. So, good evening everyone. Let's start today's session. I am Rahul Chaudhary, PMR of PhD scholar from IIT Madras. I am PMR of NPTEL TA for the course EMI, EMC and Signal Integrity, which is taken by Professor Amitabha Bhattacharya from IIT Kharagpur. So this is the 8th live problem solving session based on the lectures on week 8. So just a brief summary of this week. Uh, we have seen in the lectures covers the development of crosstalk model in frequency domain, and then we have also seen the terminal currents of a three conductor system, and we also seen crosstalk in a lossless line. Like the last lecture was about lecture number 40 was about the crosstalk in a lossless line immersed in a homogeneous medium. So we'll be solving 10 problems based on these topics that have been covered in the last week. So let's start with question number 1. So for a three wire conductor line in homogeneous medium, if L, C and R represents per unit inductance, per unit means per unit length, inductance, capacitance and resistance matrix respectively, then which of the following statement is correct? That L matrix means the inductance matrix is a symmetric matrix, R means the resistance matrix is a symmetric matrix, or third point is the product of L and C matrix is a diagonal matrix. So I hope everybody understood the problem. I will give you few seconds or few minutes to just read the question and attempt it. If you understand or if you have the answer, you can just type it here in the message. Okay, now let's begin with question number 1. So what we have given is a three wire conductor line, which is a multi transmission line problem. So in textbook they are referring these things as multi transmission line or multi conductor transmission line. Multi conductor transmission line, which is here we have a three wire conductor line in homogeneous medium. So for this course concerned, uh, we are not going beyond three wire conductor systems. So what is the given is a three wire conductor line is in a homogeneous medium, and if this capital L, C and R represents per unit inductance, capacitance and resistance matrix, then we have to comment about their uh, in matrices, means the inductance matrix, resistance matrix and the product of inductance and conductance matrix. So first is a symmetric matrix. So I think everybody knows like what a symmetric matrix is. Even if we take suppose this is Lij denotes its ith and ith element, and in the ith row and jth column of the matrix it should be equal to Lji, right? So then that matrix will be symmetric. So if we talk about the first point where it is asking that where the statement 1 says that L is symmetric matrix. So we know that the mutual inductance, let's say if between mutual inductance between wire 1 and wire 2 will be same as mutual inductance between wire 2 and wire 1. So Lij will be equal to Lji. So first thing is clear, this will be true always for a homogeneous medium in Lc and R for a 3-wire conductor system. So we can say that hence inductance matrix is a symmetric matrix. Statement 2 says that R is a symmetric matrix. R is resistance. So statement 2 says that we have to comment about the R matrix. So it represents the series conductor losses. The losses coming out because of the conductors which are in the series. It represents the series conductor losses, because what we are doing in all that is transmission line theory, we are dividing in EMI EMC also, we are dividing into per unit length resistances, small 1 2 3, and all these are in series. So it represents the series conductor losses, this R matrix, and due to reciprocity of conduction currents, the mutual resistive coupling satisfies that Rij will also be equal to Rji, which shows that R is also symmetric. So statement true is also correct. Here statement 1 is correct. Also statement 2 is also correct because R is also symmetric matrix. Because I think if you for lecture number 35 or 36, it has been mentioned there. So yeah, in lecture number 36, if you see, you can easily find it out, because there we have derived this L and R and C matrices. So R is symmetric. So statement 2 is also correct, and statement 3 states that the sum of L and C, matrix L and C is diagonal. So for a multi-conductor transmission line, or a 3-wire, in this case we have a 3-wire transmission line which is in a homogeneous, in a uniform medium, or homogeneous medium or uniform medium with let's say its permittivity is epsilon and permeability is mu for that uniform medium. So we can write L and C, multiplication of this L and C matrix as mu epsilon into I. So this I is what, like let's say for the 2 cross 2 thing, so I can write this as I2 also. So this I is the identity matrix. So we all know that identity matrix, let's say for I2, it will always be a diagonal matrix. So the element apart from the diagonal elements will be 0. So if we see, this product is giving a diagonal matrix. So statement 3 is also correct. So the product of L and C is a diagonal matrix, which is true. So now we will go to the options. Option A says only statement 1 is correct. No, because 2 and 3 are also correct. So here correct option is option D. because all the statements are correct. So if you just want to know the derivations, like how we derived these things, you can refer to lecture number 35 and 36, where professor has derived these, and you can easily understand, because this question is just asking about us to comment on the matrices. So if this is clear, we will move on to question number 2. So for question 2 and 4, 2, 3 and 4, we have a same two wire line placed over a semi-infinite ground plane separated by a distance of 3 centimeter. The height of the generator conductor is 1 centimeter above ground, and height of the receptor conductor is 1.5 centimeter above the ground plane. Radius of each wire is 12 mils. So this we have seen in lecture number 37, I think, where two wires are there which are above the ground plane. So the first, which is the generator G, I am denoting as G, and receptor R. So generator is above 1 centimeter from the ground, and the receptor one, R, is 1.5 centimeters above the ground plane. So this is our ground plane. And the radius RWG and RWR both are 12 mils. So this is what is given in the problem. Now we have to see what the question number 2 is asking. We have to determine the per unit length inductance of the generator and per unit length mutual inductance between generator and receptor. Notations have their usual meaning. Yeah. So I hope like what is the question is trying to ask is clear. So this is RWR, this is RWG, means the radius of these two conductors, which is same. So now we can take this as a mirror image between the ground, right? And we can consider these two conductors again here, and then we can solve them. So here we just have to find out the per unit length inductance. Okay, let's start with the solution. I hope this figure is clear, like what the question is trying to ask. Now we just have to determine the per unit length inductance of the generator and per unit length mutual inductance. And these formulas we have already derived, so I am directly going to use the formulas here. So in the problem it is a given that a two wire line, so this I am denoting as, for generator, as HG, and this is HR. So HG is given as 1 centimeter and HR is given as 1.5 centimeters, and separation also between them is given as, and the distance, they are separated by a distance of 3 centimeters. So I forgot to mention this one. So this separation is always center to center. This we will denote as a small s, which is 3 centimeter. So their separation distance is 3 centimeters, and both of their radiuses are same. So RWG is same as RWR, which is 12 mils. Since everything is centimeter, so we will convert this mils into centimeter, which for that we have to just multiply 12 with 0.0135. sorry 0.001 into 2.54, then it will be in centimeters. So the first part in the problem we have to find per unit length inductance of the generator. So inductance formula that we have already seen is given by Lg is equals to mu naught by 2 pi ln 2Hg divided by Rwg. So now we know everything here. Mu naught is 4 pi into 10 to the power minus 7 divided by 2 pi natural log ln of 2 times of Hg, means height of or the distance between the ground and the generator conductor is 1 centimeter, 1 divided by Rwg, which is the radius of the wire, which is 12 into 0.001 into 2.54. So I hope you can solve it now. So when we solve this, it comes out to be 0. So one good thing will be, guys, you just have the maybe I will make a mistake in the calculation. So if you have a calculator along with you right now, you can also calculate this. So because I have already calculated it and I'm just going to write the answer directly. So there may be a mistake in my solution also, so it's better you also solve parallelly and have a calculator along with you. So the answer comes out to be 0.84 microhenry per meter. And what I have seen in the options are so close, like 0.51. If we, there is a high chance that if we do some calculation mistake, this can also come. So that's why these options are closely they are written in such a way that they know what kind of mistakes we can make in the calculation. So sometime if we make a small mistake, we can get the answer as 0.51, and if we see this is coming and this is already there in the option, we will think that this is correct. So it's always better to solve the problems as much as you can, at least solve all the assignment problems. So I think if you just solve all the assignment problems before the exam, they will be sufficient. Like you can easily attempt all the exam problems. So it's a good idea to at least solve the assignment problems. So the answer comes out to be 0.84 microhenry per meter. Now, okay, in the next part of the problem, we have to find also the per unit length mutual inductance between the generator and receptor. So now this inductance of the generator, that Lg only there. Now we have to find Lm, which is the mutual inductance. So now in the problem we have to find Lm, which is a mutual inductance between the generator conductor and the receptor conductor. So for that also we have already derived, we have seen the derivation of the formula in the lecture. So it comes out to be, so I am directly writing the formula here, mu naught by 4 pi ln 1 plus h, sorry, 4 times of hg into hr divided by s square, which is the separation distance between the conductor 1 and conductor 2. So mu naught is 4 pi into 10 to the power 7, and since denominator is also 4 pi, so only thing remains is 10 to the power minus 7 into natural log 1 plus 4 times of hg is 1 centimeter and hr is 1.5 centimeter. Since both of all the quantities are in centimeters, so I'm not converting them into meters, so I'm directly writing them here. And s is given as 3 centimeters, so s square. So when we solve it, the answer comes out to be 0.05 microhenry per meter. So this is the mutual inductance between the conductor 1 and conductor 2. I hope question number 2 is clear. So if you match with the given options, so the correct option is option number D. I hope this is clear. If you have any doubt in this, please let me know. Vivek, you want to ask any question? Okay, now we will move on to question number 3. So question number 3 means the data is common. That means still we have the same two-wire line placed over a semi-infinite ground plane separated by a distance of 3 centimeters. Means this figure holds true here also. I'll just copy paste it. So yeah, means this is the same problem. The question 3 is asking if the separation between the two wires is halved. Okay, means it wants us to reduce this separation distance by reduce it to 1.5 centimeters. So it becomes half now. Then which of the following is correct? Per unit length, option A is per unit length inductance of the generator remains unchanged and per unit length mutual inductances increases. Option B says per unit length inductance of the generator remains unchanged and per unit length mutual inductance decreases. Both per unit length inductances and mutual inductances of the line remains unchanged. Option D is both per unit line length inductance and mutual inductance of the line decreases. One thing we can clearly see, if we even reduce the separation distance, why would the per unit length inductance of the generator should change? It should remain unchanged, right? Because if you see the formula also, okay, I will rewrite it here. Lg is given by mu naught by 2 pi ln 2hg by rwg. So if we see this formula itself, we can say there is no relation between the s which is the separation distance, between the conductors. So first thing is clear that option A and B, one of them should be the correct, because it says that it remains unchanged. Yes, option B also says that. Now we have to see what happens to this mutual inductance. So for that the formula was given by Lm is equals to mu naught by 4 pi natural log of 1 plus 4 times of Hg into Hr divided by S square. So it says that in the problem S has been, so S prime, I denote the new separation distance as S by 2. So if you calculate Lg, it remains the same because nothing is changed. But here something will change, because now it is, instead of 3, it is 1.5 centimeter. So Lm we can recalculate again, right? So mu naught by 4 pi ln 1 plus 4 times 1 into 1.5 divided by 1.5 whole square, the new separation distance. So when we solve it, we will get 0.13 microhenry per meter. So we see that Lg remains unchanged, but Lm is increased, right? Earlier it was 0.05 microhenry per meter, but now it is 0.13 microhenry per meter. So Lm has increased. So we will see option A says per unit length mutual inductance increases. Yes. So correct option is option A. I hope everybody understood this. If you have any doubt in this, please let me know. Okay, if it is clear, then we will move on to question number 4. Question number 4 is asking about determine the per unit length mutual inductance between generator and receptor if the separation between the two lines is doubled. Okay, so earlier what we have in question number 3, what we have done is the separation distance was reduced. Now the new separation distance is 2 times of the old separation distance, means it becomes 6 centimeters now. So same thing, we have to calculate the mutual inductance. Same formula, Lm is mu naught by 4 pi ln 1 plus 4 times of hg into hr by s square. So the best way to learn a formula or remember a formula is just solve some problems based on that. Now easily we can remember what is Lm and Lg in case of a 2 wire line placed over a semi-infinite ground plane. So definitely the questions will be from the topics that have been covered. So in textbook lot of topics are there, but in the lectures only few of them have been discussed. So it's better you go through all the lectures and solve the assignment problems. That will be really helpful for your this final exam. So now we can calculate it, right? Only thing changed is ln 1 plus 4 into 1 centimeter into 1.5 centimeter into 6 square. So when we solve it, 4 pi is gone, and when we solve it we will get around 0.015 microhenry per meter. So if we okay, so correct option is option A. I hope question number 4 is clear. So if you have any doubt from between question number 2 and 4, please let me know. 2, 3 and 4, because all are using the same formula and same two transmission lines are there. So if you have any doubt in this, please let me know. So if it is clear, then we will move on to question number 5. Question number 5, consider a lossless line immersed in homogeneous medium. Which of the following statements is or are correct? Okay, so statement 1 is chain parameter matrix is a diagonal matrix. Diagonal elements of the chain parameter matrix are equal. Statement 3 is cross diagonal elements of the chain parameter matrix are equal. So this is talking about the chain parameter matrix that has been discussed in the for a lossless line has been discussed in lecture number 14. So we can directly refer to what have been discussed in lecture 14, and I will write down the just a second. So those who have joined right now, we are discussing question number 5. So I will read it again. Consider a lossless line immersed in a homogeneous medium. Which of the following statement is or are correct? Statement 1 is chain parameter matrix is a diagonal matrix. Statement 2, diagonal elements of a chain parameter matrix are equal. Statement 3 is cross diagonal elements of a chain parameter matrix are equal. So this is talking about a lossless line immersed in a homogeneous medium. So which is something we have done in uh, lecture number 40. So where we have determined the crosstalk in a lossless line immersed in a homogeneous medium. So I will write down the chain parameter matrix for a lossless line in a homogeneous medium. So we are denoting it as phi or phi. So phi 1 is given by cos beta L into I2. I2 is an identity matrix, and phi12 is minus j omega L sine beta L. So beta L, so I'm writing it as small l, it should be capital L also. We can write it as like that. So beta L into inductance matrix L. Phi21 is given by minus j omega L, sorry, minus j sine beta L by beta L, sorry, sine beta L divided by V into 1 by mu epsilon into C matrix, and phi22 is cos beta L into identity matrix I2. So this is what a Chen parameter matrix for a lossless line in a homogeneous medium looks like. Now we will read the given statements again. Is a diagonal Chen parameter matrix is a diagonal matrix. Is it a diagonal matrix? Because if it is a diagonal matrix, only diagonal elements should have been there. Means it should have looked something like this. Sorry, something 0, 0 and some value. So option statement A is incorrect because it's not a diagonal matrix. Statement 2 says diagonal elements of a Chen parameter matrix are equal. So what are the diagonal elements here? Diagonal elements are phi 11 and phi 22. If we match them, cos beta L, cos beta, so both are them equal, both of them are equal, right? So diagonal elements of a Chen parameter matrix are equal for a lossless line immersed in a homogeneous medium. So statement 2 is correct. And cross diagonal elements of a Chen parameter matrix are equal. So these are the cross diagonal elements. If you see them, they are not equal, right? So the only correct option here is only statement 2 is correct. So correct option is option B, which states that only statement 2 is correct. I hope this is clear. If you have any doubt like how I have written this Chen parameter matrix, you can refer to lecture number 40, the last lecture for this week. So it's been discussed in lecture 40. You can see that how this matrix came. So I hope this is clear. Now we will move on to question number 6. Question number 6, okay, here also two statements are given. Consider the following statements. Statement 1 is for a lossless line in homogeneous medium, crosstalk depends on the characteristic parameters of the line. Statement 2 is eigenmatrix is a diagonal matrix. So let's move to the solution for this question number 6. So for a lossless line in homogeneous medium, eigenmatrix is a diagonal matrix, which implies that cross diagonal elements of the Chen parameter matrix depends on L and C matrix such that phi12 and phi12 and phi is directly proportional to L. Here we can see that means this is our phi12, right? So okay, I will rewrite this again. So same lossless line in homogeneous medium. So we can write the Chen parameter matrix again for this, which is given by cos beta L minus j omega L sine beta L by beta L into the L matrix, and phi21 is minus j sine beta L by b into 1 by mu epsilon into c, and phi22 is cos beta L into I2. So this is our phi11 12 phi1 21 b22. So now statement 1 says that for a lossless line in homogeneous medium, crosstalk depends on the characteristic parameters of the line. So here we can see that they are depending upon these parameters, right? L and C. I will check, use a different color. Here this L and C are per unit length inductance and per unit length capacitance, and which correctly statement 1 is true. For a lossless line in homogeneous medium, crosstalk depends on the characteristic parameters of the line. So this matrix itself talks about the characteristic impedance. So for a lossless line, from this we can directly say that it depends. Statement 1 is true. The crosstalk between the depends on the characteristic parameters of the line for a lossless line in a homogeneous medium. So statement 1 is true. And for a lossless line in homogeneous medium, eigenmatrix is a diagonal matrix, which implies that cross diagonal elements of the Chen parameter matrix depends on L and C such that, so I can write this phi12 is directly proportional to inductance per unit length inductance matrix, and phi21, these are all cross diagonal elements, right? It's directly proportional to C. And the diagonal elements of the Chen parameter matrix is real and equal. So which states that the eigenmatrix is a diagonal matrix. So now we will go statement 2 is also correct. Now correct option is option B. So both statements are correct, and statement 2 is the correct explanation of statement 1. So option B is correct. I hope this is clear. So if you have some doubt like how this came up, you can refer to lecture 40, where the professor has clearly explained this thing. Like you will get a much better idea. So now we will move on to question number 7. Which of the following represents the terminal condition at the far end of a 3-conductor line? So 4 options are given where voltages are given, and current is given at the source and at the load location. That's what 0 and L means here in the bracket. So we have to select the correct terminal condition at the far end of a transmission line or a 3-conductor line. So for a lossless transmission line, sorry, it's okay, it's a 3-conductor line. So we have to find the terminal condition at the far end, means the at the load end. We have to find the terminal condition at the far means the load end of a three wire three conductor transmission line. So I can write the general load end relation for a three uh, conductor transmission line. So at the load end, Z is L. So suppose this is our Z here, Z is 0 at the source end. So this is a usual convection or kind of notations that we use for a transmission line. So source is always represented at the Z axis. Along the Z axis, Z is 0 here, and at the load end, Z is the L. L is the length of the transmission line. Or here it's given in a capital L, like in italic. So I will rewrite this here. So don't confuse this capital L with the inductance. Generally I write it in small l, but since in the options it is given as L, capital L. Okay. So at the load end, when Z is means Z is the Z axis, we are considering this along the Z axis. So this small z is equal to this L. So I can write this voltage at the load end V will be VL, the voltage drop at the load, plus the impedance of the or the resistor or impedance attached to the load impedance ZL, as I am denoting as a matrix, and the current flowing at L. So if you think it is as a simple Ohm's law, V is equals to IR, it is something like that only, right? So this VL is the voltage drop here. So this is our load, so this is the voltage drop, and V at L is as a phasor is given by this relation. So if you match it with the given options, so here our correct option will be option number C. So you can refer to lecture number 37. It has been discussed there, like the derivation is there. So I'll just write down in a simple way, but if you need a clear derivation for it, where sir has draw a diagram also and everything, so for better explanation you can refer to lecture number 37. So here for question number 7, the correct option is C. Now we will move on to question number 8. So for question number 8, 9 and 10, data is common. Consider a two-wire line of equal diameter placed at the same height above the ground plane. Per unit length, inductance of the generator is 1 microhenry per meter. So in this problem, what is given is, it's kind of similar like 2, 3 and 4, where two transmission lines are given above the ground plane. but instead on that here both are at the same level and they have the same radius. So this is our generator. Let's suppose this is our generator, this is our receptor. Then RWG and RWR. So in the problem it is given RWG is same as RWR, and both of them are above, they are at the same height. The height is not given, so this is HG and this is HR. Okay, so the only thing in the problem which is given is LG is given as 1 microhenry per meter. So this LG is per unit length inductance of the generator. So problem 8 is, question number 8 is asking if the radius of the receptor is, okay, RWR is now is given, RWG and RWR is given as, so if the radius of the receptor is 10.62 mils, determine the height at which the two wire lines are placed. Okay, first we will convert it into centimeters. Now in the problem what we have to find is HG and HR both are same, so we have to find this height above the ground. So we will convert into centimeter, 10.62 into 0.001 into 2.54 centimeters, and in the problem LG is given. We know what is the formula for LG. LG is given by mu naught upon 2 pi ln 2 times Hg by Rwg. So now it's simple, right? We know what is Lg, which is 1 microhenry per meter. 1 into 10 to the power minus 6 Henry per meter, and 4 pi into 10 to the power minus 7 by 2 pi ln. So this Hg we have to find, and Rwg we already know it is 10.62 into 0.001 into 2.54. So when we solve it, this cancels out and this minus 7 goes through the denominator here and becomes 10, and 2 comes in the denominator, then ln 2 times of Hg by Rwg. So when we solve it, okay, since ln is the natural log, so we can take exponential on both sides. So here it will become e to the power 5, and then if we take exponential of this, it becomes 2Hg by Rwg. Move on to the next slide. So what happened here is e to the power 5 is 2 times of Hg by Rwg. So now Hg will be e to the power 5 into Rwg by 2. So we can calculate what is e to the power 5 is, and Rwg is 10.62 into 0.001 into 2.54 divided by 2. So when we solve it, Hg comes out to be approximately equal to 2 centimeters. So that means these wires are placed above the ground at a height of 2 centimeters. So the correct answer is option B. I hope this is clear. If you have any doubt in question number 8, please let me know. Okay, if question number 8 is clear, we will move on to question number 9. So here also the same line is there above height. So okay, so now in question number 9, what we have to find is if the per unit length mutual inductance between the generator and the receptor is it's given as, so last question LG was given, but here now LM is given as 0.102 microhenry per meter. We have to determine the separation between the generator and the receptor. Okay, so now in the earlier problem we have to find the height above the ground. Now we have to find the separation between the two conductors. Means now we have to find this S. So this RW is same 10.62 mils. So now we know the formula for LM, and Hg we know from the previous question because everything remains same, nothing has changed. Hg is 2 centimeters. It came from question 8. So now we can write the formula for LM, the mutual inductance between the generator and the receptor. The per unit length mutual inductance is given by mu naught by 4 pi into ln 1 plus 4 times of Hg into Hr divided by S square. So in the problem they are at the same height above the ground. That means Hg and Hr both are 2 centimeters. So Lm will be, so mu naught is 4 pi into 10 to the power minus 7 divided by 4 pi ln 1 plus 4 times of 2 into 2 because they are about 2 centimeters from the ground, and S square, S is unknown, we have to find. Lm is already known, is given as 0.102 microhenry per meter. So this minus 7 comes here, 4 pi gets cancelled out, ln 1 plus 16 S square. So this thing will become 1.02 ln 1 plus 16 by S square. So I can take exponential on both sides, so this side becomes e to the power 1.02 and this becomes 1 plus 16 by S square. So we can rewrite this as S square is equals to 16 because this can go 1 can go on the left hand side and becomes e to the power 1.02 minus 1. So this will become e to the power 1.02 minus 1. So when we solve this we will get SS it is approximately equals to, comes out to be 3 centimeters. So here the separation between them is 3 centimeters. So the correct option is option number C. I hope this is clear. If you have any doubt in question number 9, please let me know. If this is clear, then we will move on to question number 10. So for question number 10 also same data is there, means same two wire lines are there above a ground at a distance of we calculated around 2 centimeters, and the per unit length inductance is 1 microhenry per meter. So now question 10 is asking calculate the characteristic impedance of any of the wire considering free space medium given that RWG and RWR is 10.62 mils and mutual inductance is 0.102 microhenry per meter. So here now we have to find out the characteristic impedance, means ZC we have to find out. So for finding ZC we know one relation is there between, so this is the characteristic impedance and there is a relationship between this LG per unit length inductance and per unit length capacitance CG. So LG we already know what it is. Now only thing that we have to find out is CG, and then we can find out the characteristic impedance ZC, which is given by under root LG by CG. So now we have to find out this characteristic impedance, per unit length capacitance of the generator CG. So we know the formula for CM, the mutual capacitance between the generator and the receptor is given by Lm divided by V square into Lg into Lr minus Lm square. So this Lg and Lr will both be same because these two wires are exactly at the same height from the ground and their radiuses are same. So Lg and Lr means the capacitance, per unit length capacitance of this generator and per unit length capacitance of receptor both are same here because same wires are there and they are the same height above the ground, and Lm is given as 0.102 microhenry per meter, and we can find out the velocity of propagation of the wave in the free space. Since it is, we have to consider free space medium, so V also we know is 3 into 10 to the power 8 meter per second. So Lm is 0.102 into 10 to the power minus 6 divided by V square, which is 3 into 10 to the power 8 whole square. Lg is same as Lr, so here 10 to the power minus 6 into 10 to the power minus 6 will become 10 to the power minus 12, and we have to subtract Lm square, which is 0.102 into 10 to the power minus 6 whole square. So when you solve this, Cm comes out to be 1.145. So I'm directly writing, you can calculate it. So I'm directly writing the final answer, which comes out to be 1.145 picofarad per meter. But we didn't know, we don't want Cm, right? We wanted to have Cg, but we know the relation between Cm and Cg is Cm plus Cg is given by Lg divided by V square into Lg into Lr minus Lm square. So this is the relation between Cg and Cm we already find out. CG we have to find, LG and everything else we know in the problem already. So now when we solve it, CM plus CG, LG is given as 10 to the power minus 6, P is 3 into 10 to the power 8 whole square, LG into LR it becomes 10 to the power minus 12 minus 0.12 0.102 into 10 to the power minus 6 whole square. So when we solve it, it comes out to be CG plus CM comes out to be equal to 11.2279 picofarad per meter. Now we know what is CM, so CG will come out to be, CM is 1.45, so 11.2279 minus 1.145 picofarad per meter. So when you solve it, we will get 10.0829 picofarad per meter. This is our CG. But in the problem, we have to find out the characteristic impedance of any of these wires. So ZC comes out to be under root of and the ratio of LG by CG. So the characteristic impedance is given by ZC is CG. If you already know, this is 1 microhenry per meter, so 1 into 10 to the power minus 6, and CG comes out to be 10.0829 into 10 to the power minus 12 because it was picofarad. When we solve it, this comes out to be 314.925, which is approximately equal to 315 ohms. So this is the characteristic impedance. If we match it with the given option, the correct option is option D, 315 ohms. So I hope question 10 is clear. So if you have any doubt in any of the problems that we have solved today, please let me know. And I remember that we have to discuss the issue regarding the conversion from gauge to centimeter or meter, right? So sorry about that, I didn't got any time to go through that, but I have written and I will get back to you. Here also I will raise this doubt and I will also write to the professor regarding this. So next week I will clear this issue. So that's all for today's session. Thanks for joining. Yeah, thank you. Thank you all. This is all for today's session. Thank you for joining.